In this video, we'll talk about how we can represent some rational functions as power series. So let's start first with the geometric series. We know that the sum from n equals 0 to infinity of x to the power n. So here think of x as it's the ratio of the power series. We know that this is equal to 1 plus x plus x squared plus x cubed and so on. And when the absolute value of x is between when x is between -1 and 1, or when absolute value of x is less than 1, then the sum has a formula which is 1 over 1 minus x. We've seen this before when we first talk about infinite series and we considered the geometric series. So you can see something here that I can represent the rational function 1 over 1 minus x. I can write this exactly the infinite sum from n equals 0 to infinity of x to the power n. But we do have one condition here. So this doesn't work for every x. This only works when the absolute value of x is between 0 and 1. Okay, so as a result, this function, and this is nice because now you have a rational function and you are estimating, or you are writing this rational function as a power series. I mean, it's very close to it. You can think about it as an infinite polynomial, a polynomial of that never ends. Okay, so let's try to do the same for the following function. F of x equal 1 over 1 plus x cubed. So I would like to write it using the form that I have. I would like to write this as a sum of power series. So first, I need to relate this to the following sum. 1 over 1 minus x, the one that we just saw, equals sum from n equals 0 to infinity of x to the power n. Okay, now my function doesn't look exactly like this, but I can make it look like that. So for example, I have 1 over 1 plus x cubed. So I can write this as 1 over 1 minus negative x cubed, like this. Okay, so the purpose of doing that is that I'm trying to have the form 1 over 1 minus the variable. Okay, so then this can be written as sum from n equals 0 to infinity negative x cubed to the power n. Okay, so here's the complete solution. Here we have one, as I said, we're going to write the first step as 1 plus x cubed equal 1 over 1 minus negative x cubed. Then we're going to use the fact that 1 over 1 minus r, actually this is a over 1 minus r, is sum from n equals 0 to infinity a times r to the power n. This is something that we have seen before. Okay, maybe also just to recall here about this formula. Okay, we have seen sum from n equal 1 to infinity a times r to the power n minus 1, but I mentioned that it's the same thing. As you can think about it in this form, you can shift n, so you can like make a change of variable here. You can introduce m to be n minus 1. So when n equals 0, when n equal 1, m becomes 0. So the sum starts from 0, m equals 0 to infinity, a times r, instead of n minus 1 you put m. So these two are the same. You can change the index m to k or n or anything. So then here's the series. 1 over 1 plus x cubed is 1 over 1 minus negative x cubed. I replace the x by a negative x cubed. I can factor out negative 1 to the power n. So remember, negative x cubed to the power n, this can be the same as negative 1 to the n times x to the power 3n, or 3 to the power n, which is 3n. And then you have a power series. That's the power series, and this is its expansion. But we have to keep in mind, this doesn't work every time. This only works under the following condition. The absolute value of negative x cubed has to be less than 1. What does this mean? Okay. This means the following, that when absolute value of negative x cubed is less than -1, this implies that absolute value of x cubed is less than 1. The reason is the absolute value of this negative is 1, because this is like -1. Absolute value of -1 is 1. So I can ignore this. And then we have this property in general, absolute value of a to the power n, it's absolute value of a to the power n. So this is a formula that we can use. So that means you can move the exponent outside the absolute value. So this means that the absolute value of x to the power 3 is less than 1. Again, that means what? That means that the interval will be from -1 to 1, because, and this is the interval of convergence, because absolute value of x to the power 3 is less than 1. This implies that absolute value of x has to be less than 1, because if x is bigger than 1, then when you raise it to the power 3, in terms of absolute value, it's going to be bigger than 1. So our answer, our final answer is this. That's the same answer we found here, but here the interval of convergence is -1 to 1, which is equivalent to this inequality. Absolute value of x is less than 1. So we can write the rational function as a power series, but we have to identify the radius of convergence, and actually the interval of convergence, which is easy in this case because we know that I'm using a geometric series, and I know from the beginning that the ratio has to be between -1 and 1, or its absolute value has to be less than 1. Let's consider another problem. So suppose that now I have the function f of x equal x squared over 4 minus x squared, and I would like to write this as a power series, and I want to find the interval of convergence. So again, the trick is the same. I won't try to use this idea that 1 over 1 minus x is the sum from n equals 0 to infinity x to the power of n. So the function doesn't look exactly like 1 over 1 minus x, but we can make it look like that. Look, factor out x squared from the top, so you're going to have 1 on the numerator, which that's what you want. You want to have, remember, 1 over 1 minus x. So I want this to be 1, I want this to be 1, and this is going to be my variable. It's not necessarily that this has to be exactly x. It could be x over something. It could be, like the previous example, it was negative x cubed. Could be anything. In this situation, I factor out the 4 from the bottom. So when I factor out the 4, I'm going to left with 1 minus x squared over 4, or x over 2 squared. So this is my variable now. Okay. Now I can apply the fact that this is equal to the sum of xn from n equals 0 to infinity. But in this case, I don't have x. In this case, I have x over 2 square. So I'm going to put here x over 2 square. So that's going to be 2 times n. And this is the series. Okay. Now you can move, you can multiply this back if you want, because the summation, so with x is a constant with respect to the summation, since the summation varies from n equals 0 to infinity. So I can move this back if I want. So for example, I can write this as sum from n equals 0 to infinity x squared over 4, move it inside, and this can be written as x to the power 2n over 2 to the power 2n. I can further write it as sum from n equals 0 to infinity x to the power 2n plus 2 over, also the 4 can be written as 2 squared, so this can be written over 2 to the power 2n plus 2. I mean, can be written in different forms, but all of them are the same. Now, I'm still missing the important part, which is the interval of convergence. You cannot write this always in this form unless it's if x belongs to the interval of convergence. Now, what's the interval of convergence? In general, when you use 1 over 1 minus x as sum of xn from n equals 0 to infinity, you use this when the variable is less than 1 in terms of absolute value. So in my situation, I want this x over 2 square absolute value to be less than 1. Okay, now I know that this guy is positive because this is x squared over 4. I want it to be less than 1, which means x squared is less than 4. Now, if x squared is less than 4, this implies that x is between -2 and 2. So that's going to be the interval of convergence from -2 to 2. So when x belongs to the interval -2 to 2, then f of x can be written as this power series. Now, what's the advantage of writing? Now, you will see that we're not going to write only rational functions as power series. But what's the main advantage of doing this? Well, the main advantage is that the simplest functions to take their derivatives and to take their antiderivatives are the polynomial functions. And the power series are like polynomial functions, but they are infinite. Okay, so here's a very important theorem. It's related to term-by-term differentiation and integration. In general, we're going to consider a power series centered at A. You see, most of the times we choose examples centered at 0 just for the simplicity, but everything will be the same if it's centered at any value A. And suppose that it has a radius of convergence r positive. So that means it does not only converge at the center. So f of x can be written in this form, and if you expand it, it's c sub 0 plus c sub 1 times x minus a, etc. We say that f of x is differentiable and therefore continuous on the interval a minus r, a plus r. This is the interval of convergence. So the center is a and the radius is r, so it's a plus r from this side and a minus r from this side. Sometimes, I can include the endpoints, but here we're talking in general. The worst case scenario is when you cannot include the endpoints. So then I can find the derivative. F prime of x is equal to this form. How we found this? It's very simple. Look at f of x here, find its derivative. F prime of x, of course, you differentiate with respect to x. Derivative of c0 is 0. That's a constant, 0 plus. Derivative of this, it's c1 times derivative of x minus a is 1 plus c2 times derivative of this is 2 times x minus a to the power 2 minus 1 plus, for example, c3 times 3 x minus a to the power 2, etc. Okay, so in general, when you have the general term cn x minus a to the power n, when you differentiate this term with respect to x, you get n times c sub n times x minus a to the power n minus 1. So you can differentiate term by term. But how can you do? When can you do this? You can only do this if you know that the x is in the interval. So you will see now in this theorem that the interval of convergence of f prime or of f double prime or any derivative of f or higher order derivative of f and any integral antiderivative of f, it's going to be the same interval of the same radius of convergence, but the interval can differ at the endpoints. So this is how we got this formula. So the derivative is simple. You differentiate term by term. The integral is also simple. You will integrate term by term. Okay. Here's what we got here. This c is the constant of integration, and then you are integrating term by term. So you don't have to integrate term by term in this case to have a nice formula. You can just integrate the general term right here. So if you integrate this guy, the integral of c sub n times x minus a to the power n dx, this is equal to c sub n times x minus a to the power n plus 1 over n plus 1 plus some constant c. So every time you add a constant c, so we just add one constant c here. So this is the constant of integration, and then you have this general form. So this is equal to the integral of f of x dx. If f of x, of course, is represented by this if f of x is represented by that series. Okay. So this is nice. Now you can integrate and you can differentiate like we used to do. This is very important. The radius of convergence, so the radius of convergence, this is the plural of radius, of convergence of the power series in equations 1 and 2, so this is equation 1, and this is equation 2, are both R. What does this mean? This means that this converges on this interval, but for the endpoints, I don't know. I can include them. This depends. I have to check this separately. The same thing is true here. So I guarantee it's going to be between a minus r and a plus r. Now, what happens at a minus r and a plus r, the endpoints, that's something that we have to verify later. I'll show you how we can do this in some examples now. Okay. So this is the idea. To take the derivative of the sum, you can, as long as we know that the sum is convergent, so as long as we are assuming that everything is happening when the values of x are inside the interval of convergence. If this is the case, then you can interchange the summation with the with the derivative. So the derivative of the sum, even if it's infinite, it's the sum of the derivative in this case. The integral of the sum is the sum of the integral. Okay. So here I'm saying that the previous theorem says that the radius of convergence remains the same. Okay, but this does not mean that the interval of convergence remains the same. What could be different is the endpoints. That's the only difference that we can have, the two endpoints. Let's consider the following example. I have f of x equal x to the power n over n squared. I want to find the interval of convergence of f, f prime, and f double prime. Okay. Let's start with f of x first. To find the interval of convergence of f of x, I can use the ratio test. So here, I find the ratio a sub n plus 1 over a sub n. This is equal x to the power n plus 1 over n plus 1 square. I'm doing this directly times n square over x to the power n. This is equal to absolute value. I can make these as one fraction. I can simplify by x to the power n, I get x. As a result, I can ignore the absolute value here because I know that these two numbers are positive, but I don't know anything about x yet, so I keep the absolute value of x. Now, when I take the limit of this, so this, when n goes to infinity, goes to, the first term goes to 1, and this is a constant, so it approaches absolute value of x, 1 times x. Now, by the ratio test, since I'm using the ratio test, I know that the series converges when the absolute value of x is less than 1. This means what? Then the radius of convergence is equal to 1. So far, I have minus 1, 1. That's what it means. It's from negative 1 to 1. But I still need to check the endpoints. To check the endpoints. So for example, just to guarantee that, to know whether I will close this interval at some point or at the two endpoints or just keep it as is. But the radius is going to be 1, whether you include or you don't include the endpoints. So let's consider the following case. When x equal to negative 1, here's what happens. Well, actually, let's do x equal 1 first. When x equal 1, I got the sum from n equal 1 to infinity. 1 to the power n is 1, 1 over n squared. This is convergent as it's what? It's a p-series with p equal 2. Now, when x equal -1, I get the sum from n equal 1 to infinity of -1 over n squared, -1 to the power n over n squared. And this is actually absolutely convergent, because if you take the absolute value of this, you get the one above it. Okay, so if you take the absolute value of this guy, this is going to be the sum from n equal 1 to infinity of 1 over n squared, which is convergent. So it's absolutely convergent. So this converges. So then, or you can use the alternating series test, but this is easier. So this is convergent. That means the sum of -1 to the n over n squared is absolutely convergent. And then it's what? It's convergent. So as a result, the interval of convergence is -1, 1. I include the left endpoint and the right endpoint. Now I need to find f prime and I need to find f double prime. So for f prime of x, this is, as I said, this is the derivative with respect to x of the summation from n equal 1 to infinity xn over n squared. And we mentioned that we can interchange this. That's going to be the sum from n equal 1 to infinity of d over dx of xn over n squared. Now take the derivative here. That's going to be the sum from n equal 1 to infinity n x to the power n minus 1 over n squared. So then I got this, f prime of x equal sum from n equal 1 to infinity x to the power n minus 1 over n. Okay, and this is n squared. Cancel n, you got this. Okay, I know from the previous theorem, okay, so from the previous theorem, so no need to find the ratio test here. From the previous theorem, we know that r is equal to 1. So I know that absolute value of x is less than 1. I still need to check the endpoints. Okay, so we must check the endpoints of what? Because this means -1, 1. This corresponds to this interval. We must check the endpoints. X equal 1, x equal -1. Now, when x equal 1, I get the sum. So this is my series right here. This is f prime of x. I'm looking at this. So when x is equal to 1, this is going to be the sum from n equal 1 to infinity 1 over n. This is the harmonic series, divergent. So I'm not going to include the right endpoint. Now when x equal -1, I get the sum from n equal 1 to infinity of -1 to the n minus 1 over n. This is convergent by the alternating series test. So then the interval of convergence is going to be -1, 1, like this. You see, the radius doesn't change, but the endpoints may change. Sometimes they say the same, sometimes no. Okay. Now finally, I need to find f double prime of x. So using the same idea, I'm going to differentiate f prime of x. So that's going to be the sum from, okay, here I wanted to be a bit careful. N equal, it's not defined when n equal 1. Why? Look, when I take the derivative of the inside, that's going to be n minus 1 times x to the power n minus 2 over n. I do have a problem if n is negative, okay? So here always when we differentiate, you have to make sure that we always start with the lowest term to be x to the power 0, okay? If possible, we don't want x to the power negative. So that's going to start from n equal 2 to infinity, okay? In the first one, I didn't have this problem because it was x to the n. When I did when I plug in 1 here, it's going to be x to the power 0 over n, so I have no problem with this. Now, so this is f double prime of x. I know that the radius of convergent is going to be 1 according to that theorem as well. Now, I still need to check the endpoints. When x equal 1, I get this series, sum from n equal 2 to infinity n minus 1 over n, 1 to the power n minus 2 is 1. This is clearly divergent by the divergence test. Similarly, when x equal -1, I'm going to get the sum from n equal 2 to infinity n minus 1 over n times -1 to the power n minus 2. Okay, and this also diverges by the divergence test. So as a result here, the interval of convergence is -1, 1. So do you notice that for f, I mean, this is not a rule, but it happens. For f, I considered the two endpoints. For f prime, I considered only one. Sometimes nothing, so it's not a rule. But I want to show you that the interval changed, but the radius of convergence does not change. Okay. Now, I have a problem. Okay, I was able to fit everything on one page. Now I have a problem here related to the previous one. Oh wait, no, sorry. This is not related to the previous one. Okay, find a power series representation of 1 over 1 minus x squared. That's different. Okay, now you see that 1 over 1 minus x is equal to sum from n equals 0 to infinity x to the power n. Now you see that this is the square of this. It does. Okay, so if you do that, this is very hard to expand. You know, so this is not reasonable to expand. Okay, like you're gonna take an infinite sum and raise it to the power 2. This is not reasonable. So we need to think about something else. Okay, we need to be smarter here, and we need to relate this to what we have mentioned earlier. Okay, let's look at this relationship. Let f of x be 1 over 1 minus x. Then I know that f of x can be represented as sum of xn from n equals 0 to infinity, and absolute value of x has to be less than 1. This is something that we know. Now, how can I get 1 over 1 minus x squared from this? Well, let's take the derivative. What's f prime of x? If you find the derivative of this, well, you can use chain rule. I like to use it instead of this is the derivative of that one. So this is -1 times 1 minus x to the power minus 2 times the derivative of the inside, which is -1. So it's 1 minus x to the power -2, which is 1 over 1 minus x squared. So this is good news now, because the function that I want, g of x, is actually the derivative of f prime. So g of x, the one that I want, is equal to d over dx of f of x, which means it's d over dx of the sum of 1 over 1 minus x to the power 2 from n, so sum of this x to the power n equals 0 to infinity. Now I will interchange the summation with this with the derivative, so that's the sum from n equals 0 to infinity. Okay, here I want to be careful, just n equal 1. You will see why it's n equal 1. D over dx x to the power n. So then g of x can be written as the sum from n equal 1 to infinity n times x to the power n minus 1. That's the answer. Now, why I didn't choose 0? Because when n equals 0, I mean, you can put it and then erase it, but when n is equal to 0, always, when you take the derivative, the index will go up by 1. Okay. Now, I need to find the interval of convergence here. Look, this comes from... I know that the radius of convergence from the beginning was 1. Okay, so I know that r is equal to 1. By the theorem, when you take the derivative or when you take an antiderivative, it's going to be 1. It's going to be the same. So r is going to be 1. Now, you can check the endpoints. You can verify this, that when x equal 1, when x equal -1, in both cases, it's going to diverge clearly because the limit is going to be infinity or does not exist by the divergence test. So the interval of convergence is -1 to 1. Okay. So now I do have a power series representation of 1 over 1 minus x to the power 2. I can repeat the same steps and get the 1 for 1 over 1 minus x cubed, 1 minus x to the fourth, and so on. But we're going to get a better formula for this in the next chapter when we talk about Taylor series. Okay, now here's an application about this. So here's the next question is related to that one. Use the power series representation for g of x. So let's just recall what was the power series. So g of x, which was 1 over 1 minus x squared, we were able to write it as the sum from n equal 1 to infinity n multiplied by x to the power n minus 1. Okay, so I want to find the value of this series. Well, I mean, since I need to use this, then maybe I need to connect this with this. I need to connect the series that I have with that one. Okay, let's look at what we have here. I have the sum from n equal 1 to infinity, n times, you agree I can write this as this. I mean, n over 5 to the n is the same as n times 1 over 5 to the n. And also, because it doesn't look quite like that one, since this is n and this is n minus 1, I can move 1 over 5 out. And that's going to be the sum from n equal 1 to infinity, n times 1 over 5 to the power n minus 1. Now, I want you to look at this series right here. This looks exactly like that one. Okay, but instead of x, I have 1 over 5. But what's this series equal to? This is equal to 1 over 1 minus x squared. So basically, what I got here is this. That 1 over 5 is going to be carried to here. And this series is 1 over 1 minus 1 over 5. I'm replacing x by 1 over 5 squared. So this is 1 over 5 times 1 over, this is 4 over 5 squared. So this is going to be 5 over 16. 25 cancels, yes. Okay. But this is something good now because we didn't know how to find this. So the sum from n equal 1 to infinity of n over 5 to the n, it's not only convergent, I actually have its sum. This is something very rare when we talk about series, especially the sum of infinite series. Another exercise, I want to find the power series representation for f of x equal tangent inverse of x. Now, I'll try to use also, the only thing I have in my hand is this. 1 over 1 minus x is equal to sum of x to the power n. I want to use this somehow. Now, clearly, tangent inverse of x is not related to that one directly. Okay, so we need to think about something else. Maybe it's derivative. Maybe it's integral. So recall that the derivative f prime of x is equal 1 over 1 plus x squared. This is good news because this is a rational function. So this is 1 over 1 minus negative x squared, like this. So this is actually the sum from n equals 0 to infinity, negative x squared to the power n. Okay, and that means what? That means that f prime of x is equal to the sum from n equal 0 to infinity, negative 1 to the power n times x to the power 2n. Now, how this is related to that one? Now, if I want to go back to f of x, I will integrate. Okay, so f of x is equal to the integral of f prime of x dx. So this is the integral of the sum from n equals 0 to infinity, negative 1 to the power n times x to the power 2n dx. Now I can interchange the integration with the summation, so that's the sum from n equals 0 to infinity, integral negative 1 to the power n x to the power 2n dx. This is what f of x is equal to. Now when I will apply the integration, a constant will be generated, c, plus sum from n equals 0 to infinity. When you do integration, you do not change the lower limit of the summation. The integral of this, negative 1 to the power n, is a constant. You integrate with respect to x, so that's x to the power 2n plus 1 over 2n plus 1. And we added the constant of integration, as you can see. Now, one thing here we can do is, I know what's f of x. F of x is tangent inverse of x. And I can find the constant in this way. When x equals 0, okay, what's this equal to? This is f of x. This is tangent inverse of 0. Is going to be equal to c plus summation from n equals 0 to infinity 0. So this means that the constant is tangent inverse of 0, because this guy is going to be 0, which is 0, because tangent inverse of 0 is equal to 0. As a result, I have f of x equal, or let's write it as tangent inverse of x. So as a result, I have the following: tangent inverse of x equal sum from n equals 0 to infinity minus 1 to the power n, x to the power 2n plus 1 over 2n plus 1. So this is the power series representation of tangent inverse of x. I still need to determine what happens at the endpoints. Okay. Now, let's take a look at this. I need to do this on the next page, but just before we proceed, there's something we know here, which is the following: f prime of x, right here, f prime of x, that one, okay, this converse when absolute value of this variable, negative x squared, is less than 1, which means absolute value of x squared is less than 1, which means absolute value of x is less than 1. Okay, so let me write this on the next page. So f prime of x which was the sum from n equals 0 to infinity, negative 1 to the n times x to the power 2n. This converse when x to the power 2, actually negative x to the power negative x squared, is less than 1, and this means that absolute value of x squared is less than 1, and this means that absolute value of x has to be less than 1, and this means that I'm looking at the interval minus 1, 1. Or let's forget about this for now. We're looking, so this just means that the radius of convergence is equal to 1. Now when I do the integration, I'm gonna get the same radius of convergence, and I got that result: tangent inverse of x with the sum from n equals 0 to infinity, negative 1 to the power n multiplied by x to the power 2n plus 1 over 2n plus 1. Now I know that r is going to be equal to 1 here as well. I still need to find the interval of convergence. Don't say it's negative 1, 1 right away, because I still have to check what happens at the endpoints. So let's see. When x equal 1, this series becomes sum from n equals 0 to infinity minus 1 to the power n times 1 over 2n plus 1. Is this convergent? Yes. By the alternating series test, it converges. Easy to check. Now, when I plug in x equal -1, I got the sum from n equals 0 to infinity -1 to the power n times 1 to the power, times -1 to the power what? 2n plus 1, because here it was 1 to the power 2n plus 1, which is 1, over 2n plus 1. Okay, there's something here you can do. This is alternating series. If you don't really see it, you can write it like that. -1 to the n. This is -1 to the power 2n times -1. I'm breaking this over 2n plus 1. Now look at this guy here. This is equal to 1 because it's -1 to the power even. 2n is an even number. So this series is actually equal to the sum from n equals 0 to infinity -1 to the power n plus 1. Where the plus 1 comes from here. So this is n and this is 1. Times 1 over 2n plus 1. This is also an alternating series. It also converges like the previous case. So this converges by the alternating series test. So then the interval of convergence is going to be -1, 1.